98, 99, 100. Hello guys.
Hello guys.
It's Mohamad again. As you can see, today I'm grabbing the opportunity. It's quite sunny. I'm trying to stay fit. I'm working out on the rooftops. Try to grow in every moment you get. As I said in my earlier video, this time should be an opportunity for you to keep on developing. So today that's what I'm doing. In this video we're going to continue the lesson about synapses. So please stay tuned. Oh, and say hi to my children. بدكم تقوموا على البايسكلز ما حيمشي لحالك. بدكم تقوموا توقفوا بس إلكم تجوا, okay? Okay guys, say hi.
Hi.
What's your name?
Mohamad.
And Mahmoud. Okay, before we start the lesson, one more thing guys. A lot of you reached out and requested a few things. Some of you suggested that I mix things up with some Arabic and English. So why not? Let's get started. Okay, so let's get started. Synapses part 2. How the transmission happens. The mechanism. In this video, you will learn the following ideas. First of all, how chemical synapses work. And second, what is the difference between an excitatory and an inhibitory synapse. Now, the things that you need to know from before, the prerequisites, are the following. The structure of a chemical synapse and its different components. You can see details on this idea in the previous video, part 1, and in the book as well. The threshold of depolarization, and I remind you this is the minimum level membrane potential that must be reached in order to form an action potential or response. It's about minus 55 millivolts. شبانين احنا بمعدل النجاح بالامتحانات. إذا ما جبتوا ال 50 or 55 you fail. بعيد الشر أكيد. The same thing for the neuron. If it doesn't reach this level, it cannot succeed at forming an action potential or a response. You also need to know the difference between a hypopolarization and a hyperpolarization wave. I will help you remember this idea later on, but if you can do that on your own right now, it will be perfect. And ion channels, and of course how to interpret experiments. Now all these are things that you need to know. If you don't know anything about them, my advice, سكر الفيديو right now, go ahead and review them, and then rewatch the video so that you understand what I'm talking about. So, first of all, let's start with this idea. Synapses, as we saw in the previous video, control the activity of the postsynaptic cell. Like, for example, muscles. They can activate, like in the case of an excitatory synapse, or even inactivate these cells, like in the case of an inhibitory synapse. So what does that exactly mean? If you take the muscle for instance, here we see your arm muscles, the biceps here and the triceps on the other side, the biceps and the triceps. Here we have two different motions. In this first figure, we have the arm flexed, it's bent, so the action is being done by the biceps, it's contracted. At the same time, the opposite muscle, which we call the antagonistic muscle, is relaxed. It's not functioning. And when you do the opposite motion or movement, you see that the biceps is now relaxed, whereas the triceps is contracted. So what does this have to do with synapses? Recall that we said muscles are under the control of neurons through synapses. So when this muscle is contracted, this means that somewhere in the synaptic circuit and the neuronal circuit connected to it, there is activation, so we have excitatory synapses. At the same time, the other one has to be relaxed in order to allow the arm to go in this direction. So this triceps, somewhere in the neuronal circuit connected to it, there is inactivation, which we call an inhibitory synapse. The same idea here. Now this biceps muscle, to allow the arm to go in this direction being pulled by the triceps, it has to relax. So it's being inactivated. So there are some inhibitory synapses somewhere. Whereas this one is contracting to pull the arm in this direction. So it has some excitatory synapse somewhere. So the idea, what I'm trying to explain in this figure is that we need both types of synapses. When I say the synapse controls the activity of the postsynaptic cell. الكنترول ممكن يكون إيجابي أو سلبي. ممكن يكون عم نشغل الشغلة أو عم نطفيها. Both are types of control. So we have activating synapses are called excitatory بيشغلوها للسيل اللي عم تاخد الأوامر, whereas inhibitory synapses they inactivate them بيعطلوها or they stop it from working. Okay. First, interpretation of the experiments. Recall that in the previous video I gave you a couple of experiments and I asked you to try to interpret them on your own. So let's try to do that together now. But first let's review how we should interpret experiments, because you know that in the official exams and in tests, this is what really counts. You can actually understand all the experiment, but if you don't know how to write the answer, you won't get the grade. So first of all, you have to analyze the experiment, meaning you have to organize or paraphrase the given, showing clearly what are the obtained results and what did we do. There's a do missing here. Exactly, or what did we exactly do together. Okay, and then you have to write a small significance, which is a relation between the condition that was altered and the result we got. So you did kaza and this was the result. We use in the significance the following form. We say this shows or indicates or means that x, whatever x is, it does something to y. There's a relation in between. The relation verbs usually used in significances are the following. If we have a positive relation, meaning that if what I did actually activated or increased the result, this is a positive relation, we use one of these words: favors, induces, facilitates, triggers, promotes, enhances, amplifies. As you get more familiar with these words, you'll know which one is more suitable to use. Sometimes we have a negative relation by which the thing that we did in the conditions reduced the result or limited it. So we use one of these terms: inhibits, prevents, reduces, limits, attenuates, suppresses. But sometimes we also have no relation at all, meaning that whatever we did in the experiment ما كان له تأثير. So we say x does not influence or x does not affect y. So let's start with the experiment. In this experiment, we had actually 3 experiments for this document. This is the setup here. You see we have a presynaptic cell, neuron A, connected to another one B, placed in seawater. We have a stimulator at one side, and the oscilloscope recording the electric activity of these cells. So in the first experiment, an effective stimulation of the presynaptic axon A. Again, effective means it's above threshold, so it should form an action potential in A. It creates an action potential in A, no surprise here, as well as in the postsynaptic B. So what they're saying here is we apply the stimulation here on A somewhere, and we got an action potential on both A and B. Always try, guys, to with a pencil try to represent the paragraph into images, because this will help you understand it better. Trying to imagine it, imagine the ideas sometimes can be quite difficult. So how can I interpret this experiment? First of all, the analysis. We say in experiment 1, what was the result? An action potential is detected in the axon of the presynaptic neuron A and the postsynaptic neuron B or cell B upon, this is the condition, applying an effective stimulation on A. This is what we did. We applied the stimulation, we got these results. Now we go to the significance. We have to say this shows that كذا. Whatever I did, اللي عملته هون شو عطى؟ شو النتيجة تاعته؟ First of all, it's clear, it's obvious that the stimulation activated A. They already told me it's effective. The new thing here that I should conclude is the relation between A and B. So I would say this shows that the presynaptic neuron, this one A, favors the activation of the postsynaptic cell. Why did I use favors? Because there was a positive result in both. So it's an excitatory synapse. There's another part for the experiment now. Let's see what they did next. They said, on the other hand, if the stimulation is done on the postsynaptic cell B, it creates an action potential only in B. So let's imagine it on the imagine the steps on the diagram here. We apply the stimulation on B. We record the result only in B. There's nothing on A. So first of all, the analysis. I'll give you a second to think about it. Okay. So on the other hand, the action potential is created only in B when the stimulation is applied on B. Let's think of a significance. Of course, هنقول this shows that what? the thing I did, which is in neuron B, activating B. What did it do? It did activate B, it's effective, but there was nothing on A. Should I say it inhibits A, or it favors A, or doesn't affect A? So I'll give you a second, think about it. That's right. This shows that the postsynaptic neuron cannot activate the presynaptic neuron. There's no relation here, it didn't affect it. The synaptic transmission is unidirectional. This means that the message is transmitted from A to B, the orders are given from A to B, but not from B to A. Next, in the second experiment, first of all, they say here calcium ions are, this is the first time we mentioned calcium in the book, by the way, are removed from seawater in which the two cells are found. Then a stimulation of the presynaptic neuron gives an action potential in neuron A. So let's imagine the steps here. First of all, we're kicking the calcium out. Get the hell out of here. Yalla man hon. Allah ma'ak. So now the water is, or the medium is calcium free. Then we apply a stimulation where they said on neuron A. So we apply the stimulation on neuron A and we get a result only in A. This is similar to the first experiment. The stimulation is on A, but this time with no calcium in the water, the result is only recorded in A but nothing on B. So let's start with the analysis. In contrast, because we have a difference in the result, an action potential was recorded only on neuron A when calcium was removed from the medium before applying an effective stimulation on A. So now we get to the significance. What should I talk about? Of course, this shows, indicates, means that what? What's the variable that I changed here? It's exactly calcium and its relation with the synapse. Without it, the synapse did not work. So I don't want to talk about its absence. When I'm giving significances, I should talk about its actual role. So the significance should be, that's true. This indicates that calcium facilitates synaptic transmission. If you said this shows that removing calcium stops the synapse, technically it is correct, but you're just repeating the experiment or the analysis. When we do a significance, again, we're trying to come up with rules or with natural relations. So the manipulation I did, removing the calcium, was a step to discover what the role of calcium is in real life or in vivo. So the relation should be the role of calcium in normal synaptic transmission. It facilitates it, makes it happen, makes it easier, allows it to happen. It's important for the process. Let's continue the experiment now. The next thing they did, they said second, calcium ions are injected inside of the presynaptic terminal, and in the absence of any stimulation, a response is recorded in B. So, okay, what are you going to do with that? This is calcium. We're going to inject calcium into the presynaptic terminals from outside into the cytosol of the synaptic terminals. So again, this is what we're doing here. What happens? We get an action potential only in B. So let's start with the analysis. In contrast, an action potential this time was recorded in neuron B when calcium was injected into the presynaptic terminals, and despite the absence of any stimulation. Notice that we didn't apply any stimulation neither on A nor on B in this experiment. We only injected calcium to the inside. So the actual action here is the entry of calcium into the presynaptic terminals. So this entry of calcium was able to activate B. So the significance would be, this indicates that the entry of calcium ions into the presynaptic terminals triggers the synaptic transmission. Notice that I didn't say injection of calcium. Entry and injection are a bit different actually. Injection is something that we're doing in the experiment. Entry would be something that naturally happens inside the living body. Next, experiment 3. In the third experiment, in the absence of any stimulation again, the addition of a small dose of acetylcholine in the synaptic cleft produces a response in B. However, the deposit of increasing doses of acetylcholine gives in B the recording of document E. So we have plenty of data here. Let's try to understand them one by one. So first of all, the crazy scientist here is saying that acetylcholine, the substance they mentioned here, is extracted from the presynaptic vesicles. So it's a chemical found in the presynaptic neuron. أخذ, what did he do with it? We inject it into the synaptic cleft, meaning not inside the synaptic terminal this time, in the space in between, بالنص بيناتهم, like so. So what happens? A response is recorded in B. So let's analyze it. A response is recorded in B upon the injection of acetylcholine into the synaptic cleft. What's the significance about? Of course, about acetylcholine. So acetylcholine facilitates the activation of the postsynaptic cell. Its presence activated the synapse. What else did they say? They said, however, the deposit of increasing doses, the injection of higher doses or concentrations of this molecule, gives in B the recordings of document D, this one. So you notice that as we're increasing the dose, what's happening? What are these, first of all? These are, yes, you guessed it, hypopolarization waves or a graded potential. You remember we said that a graded potential is a potential with variable amplitudes. So the amplitude of these waves is increasing as the dose is becoming higher. So the analysis would be, furthermore, the amplitude of the recorded hyperpolarizations or responses in B increases as the dose of deposited or injected acetylcholine is increased. So we already said that acetylcholine facilitates the activation of the synapse. Now what we're seeing is that its effect actually is related to its concentration. The more you have, the higher the response. So the significance هتكون, this shows that the stimulatory effect of acetylcholine is proportional to its dose. بس تزيد هيدي الكمية بتزيد الإفكت عادي. A bonus experiment. So this is something you might see in the exercises or in the exams. أعطيكم إياها ببلاش بدون علامات. So they said no response is recorded in B if the injection of acetylcholine is preceded, يعني قبل صار, an injection of antibodies specific to certain proteins on the surface of the presynaptic cell. There's a lot to understand here. They're saying antibodies block the function of molecules to which they bind. So let's see it in a diagram here. This is the synapse. This is the acetylcholine they injected. But before doing that, they had injected something called an antibody, which are immunological molecules which bind to proteins and block their function. So what we're doing here, we're blocking the function of these proteins on the postsynaptic cell, and then we're injecting the acetylcholine, and this prevented the acetylcholine from working because we got no response here. So what does that mean? It means that هدول الأوادم هون البروتين are what they are necessary for the function of acetylcholine. So the conclusion would be acetylcholine must bind to these postsynaptic proteins in order to activate the postsynaptic cell. بدون ما تعلق عليهم أو تشتغل معهم, it cannot work. Summary of the conclusions that we got out of these experiments. First of all, the stimulated presynaptic neurons can activate the postsynaptic cells. This is in the first experiment. But the opposite is not true. The post cannot activate the pre. Okay? Next, calcium ions must be in the medium. Without them, the previous step or the stimulation of the presynaptic neuron is useless. Then, these calcium ions must enter into the presynaptic terminal. Chemicals like acetylcholine we just mentioned are released into the synaptic cleft and can activate the postsynaptic cell. And the more of them released, the more we have, the more important is the response. And these chemicals, to function, to work, they must bind into or on postsynaptic receptors. Now, in the book, this is the summary of the conclusions. So I'm going to read it quickly just so that you get to form an idea. And the diagram actually relates to the paragraph. So the transmission of a nerve message in the chemical synapse. I'm going to go through it or skim through it quickly. First of all, we have the first step, arrival of the action potential. The action potential has to arrive. Then we have something related to calcium, it's entering. Then what happens in step number 3, after the release or exocytosis, we have the neurotransmitters are binding on specific receptors. Then we have chemical dependent channels located on the postsynaptic membrane. This will modify the membrane potential, etc. A lot of data here. So I'm going to take my time and explain them one by one. So This is, I think, a simpler way. For the message to be transmitted from the presynaptic to the postsynaptic neuron, first of all, the action potential must arrive at the action terminal. Here it is, step number 1. The next step, voltage-gated Ca2 plus channels open. So here we have the how calcium actually enters. We have channels for calcium, and these calcium channels are actually voltage-gated, meaning that they open by a certain voltage. يعني بيفتحوا على الكهرباء، بيبقى على الكهرباء. وأي كهرباء, which electric current here or electric force is acting, it's the action potential. The arrival of the action potential, bringing voltage here, will change the voltage at this site, opening these channels. Calcium in the outside or on the outside of the neuron is in higher concentration, so it starts to fuse along the concentration gradient to the inside. When calcium enters, so calcium enters the presynaptic neuron, what happens? The calcium signals to the neurotransmitter vesicles, the synaptic vesicles, so that they, in step 5, move downwards and dock on the, يعني بيرسوا, on the presynaptic membrane. And then in step 6, we have the release of the neurotransmitter by exocytosis. Then the neurotransmitters are in the synaptic vesicle, in the synaptic cleft, I'm sorry. They bind on the receptors, the proteins on the postsynaptic membrane, and they initiate the postsynaptic potential. Okay? So these are the ideas that you should memorize from the book, but I think we can elaborate a bit more to make them more clear. First of all, what happens when the neurotransmitter or the neuromediators bind to the postsynaptic receptors? There are some important ideas that you should note here and recall. First of all, the threshold of depolarization. We said it's the membrane potential, minus 55 millivolt, that must be reached in order to activate a neuron. So you can, if you remember this diagram here from the previous activities, this is the threshold here, minus 50, minus 55. Waves or membrane potentials that do not reach the threshold, ما بوصلوا لمعدل النجاح, they will simply fail and will not form action potentials. Only those that reach the threshold of depolarization will succeed and will form action potentials. So this is the first idea. The second, the difference between a hypopolarization and a hyperpolarization. A hypopolarization wave is a small wave showing a decrease in the internal negativity of the cell. So what about a hyperpolarization? It is a small wave showing increase in the internal negativity of the cell. Look at this diagram here. We have two different waves here. Of course, when it's at minus 70, it's the resting potential. When the membrane potential gives this shape, lifted upwards towards 0, closer to 0, it's actually becoming less negative, because minus 70 here you can see it's almost minus 60. So it's less negative. So we say it's a small depolarization, or better, a hypopolarization. So the negativity has decreased. Whereas in this wave here, you see that it becomes more negative, going towards minus 80 approximately. So here we say it's a hyperpolarization. So this is a hypopolarization, this is a hyperpolarization. And the last idea, some ion channels can be gated. They can be controlled by voltage or by binding of a particular molecule or a ligand. So here we see different types of ion channels. Some ion channels are always open, so they don't have a gate. They're open all the time. So they allow K plus or N plus or whatever ion related to them to enter or exit. Others are gated, meaning that they close and open upon particular conditions. These ones are called ligand gated. The ligand is the molecule that binds to them. So in this case, a neurotransmitter, for example, can bind or in another molecule to open the channel, and when it's removed, the channel will close. Some of them are mechanically gated, like we saw in the document number 4 for the Pacini corpuscles sensitive to pressure. They are actually activated by pressure. When pressure is applied, these channels open. When pressure is removed, they close. And the voltage gated channels, which open upon the change in the voltage, like the calcium channels we mentioned a second ago. Now, what else? So these are the 3 ideas that you need to know. Let's go to what happens when the neurotransmitter binds. First of all, we'll start with the case of an excitatory synapse. The membrane potential in an excitatory synapse should approach the threshold of depolarization. How come? We're saying it's excitatory, means it has to try at least to form an action potential or to give a response. And to do that, it has to reach the threshold of depolarization. So in that case, to achieve that, usually this is achieved by the opening of ligand-gated Na+ channels. So when it's excitatory, usually Na+ channels are opened by the binding of the neurotransmitter. Na+ being more outside will enter, making the inside of the neuron of the postsynaptic cell less negative. So you see this wave here, it's exactly a hypopolarization. It's becoming less negative and thus approaching the threshold. So هون it's being excited. عم نشجعها، عم نحمسها انه توصل towards the threshold. So you can do it, yes. Even if it doesn't reach the threshold, it's still excitatory. What do we call this wave? You can call it a hypopolarization, but to be more precise, we can call it an excitatory postsynaptic potential. This is an exclusive name for synapses. It is excitatory because it's approaching the threshold, coming closer to -55. It's on the postsynaptic membrane potential, so we call it excitatory postsynaptic potential, or EPSP. What about the case of an inhibitory synapse? This should be inhibitory here. I'm sorry, so we have to get this fixed. In case of an inhibitory synapse, sorry, disregard this one here. Let me fix it. Actually, I can do that in a second. In front of you. Okay, inhibitory. Got it. So back, now it's fixed. Excellent. So in the case of an inhibitory synapse, the membrane potential should approach the threshold. So it shouldn't approach, I still need to fix it. It should go further away. Okay, I'm stuck this one. And now I think it's perfect. So in the case of an inhibitory synapse, the membrane potential should go further away from the threshold of depolarization. So this is achieved usually by the opening of ligand-gated Cl- or K+ channels that allow Cl- to enter or K+ to exit the postsynaptic cell. Thus, the postsynaptic membrane is made less negative. So let's see how that happens. To make it more negative, we can open Cl- channels. So Cl- will enter, being more on the outside, more negative inside, making the membrane more negative. So it's going towards the negative more. This is a hyperpolarization, further away from the threshold above. And we can do the same thing if we open K+ channels, because when K+ exits, it will make the membrane less positive inside, so it's more negative, so also the same result. What do we call this wave? We call it, go ahead, think about it. It's an inhibitory postsynaptic potential, a hyperpolarization, but the more appropriate name is inhibitory postsynaptic potential, or IPSP. The end step is coming right up. So got you right there. You thought I'm done with the video. We still have one more idea. How does the synaptic transmission end? It can end in one of these three ways, actually. First of all, some of the neurotransmitters will diffuse away from the site, from the synaptic cleft, but most of them will be either degraded, broken down by enzymes, or they might be reabsorbed, or we have reuptake by the presynaptic neuron. In all three cases, the neurotransmitter is no more available to bind on the receptors, so the postsynaptic cell will stop functioning, or the synapse will stop. So now this is the summary of the lesson. It's the same idea, we just added the last two steps here. So these are the points that you need to memorize. I would suggest that you copy them on your copybooks to make it easier for you to revise. And finally, application and practice. I do suggest that you check out these sessions, 2018, the first one, exercise 3, and 2019, the first session, exercise 2. You can visit crdp.org for all these sessions. And that's all, folks. Thank you very much.